right, so our last speaker, last but not least, as Turnkey Systems Manager at Bloomy, Grant Gothing is responsible for hardware and software standardization and reuse across all of Bloomy's automated functional test systems. So in addition to R&D efforts, Grant gets involved in sales, training, and even built his own custom ATEs from time to time. Luckily for us, he's also a certified LabVIEW architect, so that's good for us. Grant's going to spend some time talking about developing code and then deploying that code, so to kind of finish off the solution, the ultimate goal of deploying a successful deployment. So I'll hand it over to Grant.
Thank you. Can everyone hear me? Good. So once you've defined your requirements and you've selected your hardware, it's time to implement your code. At the heart of your test sequencing, or at the heart of your software is the test sequencing framework, which typically, we're at an NI conference. Usually I tend to choose LabVIEW or TestStand for this. But essentially what a test sequencing framework is it allows test developers to string together code modules and flow control in order to create a complex test sequence. These code modules can be very simple things like interacting with low-level drivers of the UUT, or more complex code that's such as hardware abstraction. The test sequencing framework also allows you to implement property files for limit generation and modification, as well as result processing to configure how your results are presented to your manufacturing engineers and your operators. Oftentimes a test sequencing framework, or most of the time, it'll also have a test development environment where your engineers can develop these sequences, and a runtime operator interface or an execution environment where the operators can run these sequences to ensure the validity of the unit under test. So because the test sequencing framework is so important to the ATE software, let's just take a look at some of the common features of a good test sequencing framework. I personally have written probably 2 or 3 different frameworks in LabVIEW, and I've used a few others that are text-based. And in the end, I found that once I discovered TestStand, it's really helped me in a lot of the test development that I've done. It gives you a lot of stuff out of the box, like this developer and runtime interface. It has an open API that really allows you to access any of the low-level features that you might need in order to execute your test sequence. It gives you the property and limit files, stuff that I talked about, and it provides a really easy interface for test developers to develop their tests and for operators to run them. And furthermore, because it's such a widely used application, there's a lot of support and examples built into it that allow you to get the help that you need along the way. So once you've defined your test sequencing framework, it's time to develop the code. The first step in developing your code is to understand the framework that you selected. So in the case of TestStand, there's a whole lot of options just out of the box. Because it's so flexible, you need to understand what these options are and which ones maybe need to be modified for your particular application. So to start, what type of test are you running? Are you running a single up test, sequential, run product after product after product? Or are you doing something that's more multi-up? So you could do a parallel model where you have individual UUTs being tested asynchronously, or a batch model where everything runs from the top down to the bottom and starts and finishes at the same time. Oftentimes you'll need to configure your reporting, so your different departments may have different reporting requirements. And by defining that up front, you'll understand what your end goal is and be better able to serve your customers. So the overall purpose of writing this test sequencing software is to utilize the instrumentation available to you that you've already selected and in the connections that you've selected in order to implement a test procedure to test your unit under test. So the key to this is to make your sequences easy to read and easy to follow. In TestStand, there's probably 100 different ways to do the same thing, and some of them may be more intuitive than the others. So for instance, flow control, you can use preconditions and post actions and pre-expressions in order to jump all around your test sequence, but it's not always intuitive when you go back to look at it. But if you use explicit flow control like for loops, if statements, case structures, it allows the operator or the developer to more easily see what you did. And if you go back a year from now, using explicit flow control will make your life a lot easier and make your test sequences a lot easier to follow. In the end, you really just want to make your test sequence read just like your test procedure. So as much time as you, the developer, or your test engineers spend developing these test sequences, the operator is going to spend a lot more time with it. Hopefully, as long as your product has some good longevity with it. So you want to code for those end operators. If you use a test sequence or a test step name like measure DMM at mux channel 7, and that test fails, the operator's not really going to have any idea as to what that means in relation to the unit that they're trying to test. So a better name might be verify 5-volt rail on TP7. That way, if that step fails, the operator is going to see that in the report and know the general area of the unit that they're testing, where that error might be and how to fix it. Furthermore, from the operator standpoint, the test development environment gives you a lot of access to breakpoints and flow control and single stepping. But a lot of this can be really overwhelming to an operator that may have a fast turnaround time. So using an easy, intuitive GUI with maybe a few buttons, I usually like to say start, stop, and pause. And pause is almost optional. Gives them the confidence that they know how to test the unit. If they can put it on, keep the keyboard, keep the mouse out of it. You know, if you can do everything with touchscreen and a barcode, it's going to make the operator's life a lot easier. And in the end, its support will be a lot smaller. So finally, nothing's ever set in stone. So you kind of need to plan for changes. By breaking limits off into a property file, you're able to loosen or tighten them up as needed. If you need to test a different family of products, so for instance, you have a 24-volt product and a 28-volt product, you may not need to change any of your actual test sequence, but by breaking all those properties and limits off into a file, you could more easily adjust them as needed without having to recompile your test code. And if possible, a big thing that I'm a big proponent of is hardware abstraction. And by implementing hardware abstraction, you actually reduce the coupling between your low-level code and your test sequence code. So you can have test developers writing test sequences while hardware engineers are developing the hardware in parallel. That'll speed up your test development time, and it also makes it a little bit easier if you have an instrument go obsolete or fail. You can swap something else in without affecting your high-level test code. Question?
Two questions. Talking about limits, is it possible to have test stand pull limits from like a database?
Yes,
rather
it
than-
definitely is.
Okay.
Yep.
And then on the hardware abstraction, is that abstraction layer in testing or is it in your lab code?
So
Testing?
typically I implement, it's kind of a little bit of both. In the one that I've worked on at Bloomy, we have something we call a hardware access framework. It's just our own internal one. There's underlying lab code that implements all of the functions of the hardware abstraction, but on top of that, we built in custom step types in test stand that allow a more easy interaction with that, so that your test developers don't actually need to understand the low-level code. They just see it kind of like a wizard that pops up. And so it's kind of on both ends.
Is there, like, has NI published, like, is this how you do hardware abstraction? Or is that like it's totally a Bloomy custom thing?
The one that I use is custom, but I think there are some best practices available. Yeah. Good. So code development is one thing. Deployment is a whole other thing. When you get into the runtime engine, when you get into deploying to, maybe you have one system across the hall or 100 in another country. There's a lot of implications to going to a runtime engine versus the test development engine. And so Teststand gives us, or with Teststand you have these workspaces and projects available to help you organize your system. And by using those you get the Teststand deployment utility, which is essentially a build script that allows you to create an installer that you can use to install on each of your deployment systems. And that utility allows you to pull in dependencies, code modules associated with each of your test sequences, so that it's more easily, so you have a better chance of deployment success down the line. A few things that you can do to still improve that on top of that deployment utility is making sure that all of your test sequences use relative paths. In Teststand, you can choose when you put down a LabVIEW VI or some sort of code module, you can choose an absolute path, a relative path, or to add the search directory. Typically what I like to do is set my search directory to the root of my project at the beginning, and then use everything relative to that. And that way when you go to deploy, you have a much better chance of everything being based off of the same relative path, rather than having your development machine be different than your coworker's development machine being different than any of your deployment machines. So relative paths are a good thing. I don't think I've ever used an absolute path and said that was a good idea later on. And finally, deploying compiled code is something that I've really gotten into the habit of in the last probably 2 years. LabVIEW now has these packed project libraries, or LBlibP, and essentially it's kind of like an old LOB, except it allows you to pull in that code into a more hierarchical structure. You can have folders inside of it, and it pulls in dependencies as well. And the benefit of that is it allows you to run compiled code. You can deploy a single file instead of a folder full of hundreds of files. And by deploying that compiled code, you run into less issues when you switch over to a runtime engine versus the development environment. So, beyond just the software, deployment is often a huge undertaking. Installers can take several days to perfect. Sometimes you need to pull in hardware documentation from multiple sources. You need to make sure that you have an ATP that you can use for sign-off. And so, including deployment into your budget, including it into your schedule, can really eliminate a lot of that last-minute stress. Going back to the installer, if you understand what the build process is, how to use that testing and deployment utility, and actually start running your build scripts early on, you're going to save a lot of time in the future, where if you have hundreds of VIs, dozens of sequences, and you go to deploy it and you get a laundry list of failures, it's really hard to pinpoint where those might be. But if you have a single sequence with a code module and you figure out your build script and then you slowly add on top of that, it's going to be a lot easier to understand where your failures might occur. Furthermore, even by deploying compiled code, the runtime engine still sometimes can behave a little bit differently. So you may need to understand some more low-level debugging practices, such as the desktop trace execution toolkit, or maybe you just need to put dialogues into your VIs in order to pop up and tell you what's going on. Sometimes it's just there's different behaviors there. Understanding what your deliverables are. So different industries, different customers, different departments have different requirements. If you're deploying this into an FDA environment, you may have months of validation testing, where if this is a low volume consumer product, it may be a quick, easy ATP. You run through, make sure you can get some passes and do some fault insertion, and everyone's happy. So understanding what those requirements are in terms of deployment and software, hardware, documentation deliverables is really important from the start. And then finally, just test the system as much as possible. Don't leave test to the very end. Test it incrementally along the way. And if possible, bring someone else in who's external to the project to come in and try to use the system and build it. Oftentimes, managers are really good at this because they are going to see your project from a different standpoint. They're going to try to do things that you would never think of, and when they don't work and you say, well, I wouldn't expect anyone to use that, that's something an operator may do. So for instance, if you have an e-stop button pushed in and you run your test, you may get a runtime error. To an operator, that might be a catastrophic failure. So being able to catch things like that, some things that you might not have thought about, is really beneficial to keeping your system easy to use. And ultimately, the whole goal is to get sign-off on the